Good afternoon. Today we're going to work on Chapter 10.3 notes, and you're going to be extending your knowledge of hypothesis testing to hypothesis testing for population mean. So let's go ahead and turn in our course back to page 235. So here we are. This page actually is what should be printed from page 268 in your yellow sheets, testing hypotheses regarding a single mean mu. And it would be this is for using a t-test in your calculator, but we are actually going to be doing this lesson with statcrunch. So the statcrunch instructions are going to stat, t-stats, and then one sample. And that's because t-stats is being used. Remember back in chapter 9, we talked about we have to use a new little bit different curve called the t-curve that's a little bit more spread out than the normal curve. Very similar, but a little bit different because we're actually estimating both the mean and the standard deviation. So let's go ahead and flip to page 236 with our first example here. And so this says the average credit score in 2019 in the US was 703. A researcher for Capital One Bank believes the credit score for their customers is different than this value. They gather the credit scores for a random group of Capital One customers. There are 19.6 million Capital One customers in the US. So that's your population size N. And then I put this StatCrunch data in, so you can go find that, and then we're going to verify that our conditions are met. So let's get started on verifying our conditions in A, and then we'll hop to StatCrunch to look at our data. So is our sample random? Yep, a random group of Capital One customers. And then 2 is independence. And so for independence, we have to show that our sample size is less than 5% of our population. So our sample size was the sample right here, and there are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. So our sample size is 28. So 28 has to be less than 5% of our 19.6 million customers. And 5% of 19.6 is 0.98, so 980,000, and it's definitely less than that, so we should be good. And then our third thing for normality is our a little bit different than 10.2. 10.3 is just if our sample size is bigger than or equal to 30, or we have to look at a normal probability plot. Well, our sample size is not bigger than 30. It's only 28. So we have to use our plot. And our normal plot looks linear. So we're going to give it a check because normal plot is linear. Conduct the hypothesis test at the 0.05 level of significance. Confidence interval for mu. So not a confidence interval. It says conduct the hypothesis at the 0.05 level of significance. For mu. So it says show all steps, graphs, formulas, and substitutions. So it says researcher for Capital One believes that the credit score for their customers is different. So that's what we're going to be testing, that it's different. So our first step is H0, H1, and we're testing about a mean, so we have to use the mu symbol. And they think that the average is 703 from back in 2019. But the researcher thinks that it's different. So we're going to use the not equal to, because the researcher believes that it's different than that value. So it's different than 703. Our level of significance alpha is equal to 0.05. And our test statistic is now called a T0. So T0 is equal to X bar minus the mu 0 over the standard error, which is S divided by the square root of N. This is going to come out of StatCrunch. We don't have our sample mean because that's from our data right here. But our picture is going to be reflective of our hypothesis statement. And so it's two-sided, so we have to draw our picture accordingly. And then we're going to get our p-value from StatCrunch, and we're going to compare that to alpha of 0.05. And then we're going to state our conclusion. So let's go ahead and go to StatCrunch and find our data. Okay, so we are at our data here. It's under bar 2, so we have to remember that. And so to run our hypothesis test, we're going to go to stat. And remember, we're choosing t-stats. One sample in with data. We actually have data we put in, and that data is in bar 2. And then our hypothesis, we said we think the credit score should be 703, but the researcher thinks it's not equal to 703. Oh, 703. And the researcher thinks it's not equal to 703. So we're going to hit compute, and there is our output. Our T statistic is a negative 3.1, negative 3.213, and our p-value is 0.0034. Okay, once you have that written down, our sample mean, just for us to have, is 634.6. So let's go back to our paper and make sure we're all writing the same information down. So there's our T statistic, there's our p-value, which is spread out amongst these areas. It is definitely less than our alpha, so we do reject H0. So in that case, there is sufficient evidence. So there is sufficient evidence to support the claim that the average credit score of capital 1, because remember that was our population, capital 1 customers is different than 703. Completed your first hypothesis test for the testing for means for quantitative data. Yay. So our last example we just did a couple here for 10.3, it's page 237. It says, understand the difference between statistical and practical significance. So in Canada, the average age of a patient admitted to the intensive care unit in 2000 was 64.5 years old. The hospital administrator believes the age of ICU patients has decreased since then. They gather a sample of 6,018 random ICU patients over the period of a few years and find the average age of the ICU patient to be 64.28 years with a standard deviation of 8.2. Are these results statistically significant at the 0.05 level of significance? Assume the conditions needed to conduct the test are met. So we're going to do a hypothesis test. And we're testing that they think the mean age is 64.5. But they believe the age has decreased, which would be less than 64.5. And the alpha is level of significance of 0.05. And so our T0 we will get from statcrunch. Our picture is going to be a left-tailed from our hypothesis. And then we'll be getting our p-value from statcrunch, and we're going to compare that to 0.05. And then we'll state our conclusion. So let's hop back over to statcrunch here. And this time we're going to go to t-stats, one sample with summary. So we're not using the data that we have here. We're just using our sample mean that we got from the age of these patients, 64.28. Sample standard deviation was 8.2 years, and the sample size was 6,018. And we're testing, they think the age is actually 64.5 from historical things, historical data, and then we're testing that it's less than 64.5. So there is our output. And there's our T statistics, so go ahead and write those down. And we will go to our paper here. So our test statistic is a negative 2.08, and our p-value is 0.0187. So let's compare that to our alpha that we had discussed. So compared to our alpha 0.05, it is less than, so we do reject H0. So there is sufficient evidence to conclude or to support the idea of to conclude that the average age of ICU patients is less than 64.5 years. Okay. Because the sample was 64.28. And it doesn't seem like much, but I guess there's enough evidence, barely, right? It says, are the results of great practical significance in this situation? I would say no. I mean, does the average age really matter? I mean, it might tell you something that maybe older or younger people are having medical conditions that are putting them in the ICU, but I don't know that it really has any practical significance. So that's what's important to understand, is just because data shows that we have sufficient evidence to support a claim using a level of significance of whatever we suggest doesn't mean that it's practically significant. So that's what our warning here is about here on the bottom of page 237. When a result has a small p-value, we say that it is statistically significant and reject the null hypothesis. But that does not always mean that the result is important. When a result is statistically significant, we can only conclude that the true value of the parameter differs from the value in H0 in the way specified by H1. We cannot conclude that the difference is large enough to be important, i.e., it might not be a practically significant result. So that's important to remember. So have a blessed day, and I will catch you back for Chapter 11.